64 feet tall, built into the building itself because nothing else could contain it. The Roebling rope closing machine wasn't just big, it was the building. You couldn't separate the two. The factory floor was designed around this monster, walls rising to meet its height, because when Charles Roebling designed it in 1893, he wasn't thinking small. 80 tons of wire loaded for a single session, 30,000 feet of cable, spun without a single splice. One continuous rope that could hold a bridge or stop an elevator from becoming a coffin. Every suspension bridge cable in America. Every mine hoist that kept men from plummeting into darkness. Every elevator in every skyscraper that shot toward the clouds. If the rope failed, the bridge fell. If the rope snapped, the elevator dropped. This machine made the rope that held the country together. It was a masterpiece of industrial engineering. It was also the beating heart of an empire built on twisted steel. Before we're done, you'll understand why this machine became inseparable from the building that housed it and what it cost the men who kept it running. We're going to find out how they built a machine so large it became part of the architecture, and what it took to keep feeding the beast that fed America's skyline. We're going to see the wire snap and the bodies fall. We're going to stand in the factory when the tower screamed. This is the story of the rope-closing machine, and the men who couldn't let it stop. When hemp killed horses, Trenton, New Jersey, 1848. Along the Delaware and Raritan Canal, John Augustus Roebling bought 25 acres of mud and ambition. He'd come from Germany 15 years earlier with an engineering degree from Berlin Polytechnic and a head full of theories about wire. Not the delicate kind, the twisted, brutal kind that could replace the hemp ropes that were strangling American industry. Hemp rope had a problem. It rotted. It frayed. It snapped without warning. In 1848, a British mining journal documented 415 deaths in English coal mines, 89 of them from rope and chain failures alone. Men dropped into shafts. Loads crashed. Families lost fathers because organic fiber couldn't handle what iron demanded. The numbers were grim, but they told only part of the story. Every hemp rope failure was a family destroyed, a widow left with children and no income, a mining company facing lawsuits and shutdowns, an entire operation brought to a halt because the only thing holding tons of ore or dozens of men had given up and split apart. Roebling had seen it himself in Pennsylvania. Horses dragging canal boats over the Allegheny Mountains on the Portage Railroad, straining against hemp ropes on steep inclines. One day in the late 1830s, he watched a team of 5 horses lose their footing on wet cobblestones. The rope snapped. The load slid backward. All 5 horses were dragged to their deaths in a tangled heap of harness and screaming. The image stayed with him. Not just the horses, though that was bad enough, but what it meant. If hemp couldn't hold a canal boat on a slope, how could it hold a bridge? How could it lift a building's worth of iron and stone? How could American industry scale up when the very ropes holding everything together were made of plant fiber that rotted in the rain? He remembered a German engineering paper about experiments with wire rope. Not one thick cable, but multiple thin wires twisted together, each carrying load, each backing up the others. If one wire broke, the others held. Redundancy through geometry. It was elegant, it was obvious, and nobody in America was doing it. By 1841, he'd built his first wire rope at a farm in Saxonburg, Pennsylvania. Crude, made with second-hand equipment. But it worked. He pitched it to the State Board of Public Works in 1840. They passed. In 1841, he finally sold his first batch to the Pennsylvania Canal Construction Project. The rope was rough, the equipment was improvised, but the rope held, and it kept holding. That first rope measured 1¼ inches in diameter. Not impressive by later standards, but revolutionary for its time. It was more convenient than hemp, more durable, and it didn't rot when it got wet. A year later, he had his first U.S. patent, number 2720, Method of and machine for manufacturing wire rope. The patent described a method of spiral laying of the wires around a common axis without twisting the individual wires, while keeping them each under a uniform and forcible tension. The innovation was in the tension. Previous attempts at wire rope had suffered from uneven stress distribution. Some wires carried more load than others. When the overstressed wires broke, the whole rope failed. Roebling's system used weights and swivels to maintain uniform tension on all wires during the twisting process. Every wire carried its share. Every wire could be trusted. The old way? 100 men pulling hemp for a month to move what needed moving. Roebling's way? Wire rope that could haul the same load in days and do it again next week without rotting. The revolution wasn't just strength, it was reliability. You could trust it, not to kill you, but making wire rope on a farm wasn't enough. The demand exploded. Suspension bridges, elevator shafts, mining hoists. The entire vertical ambition of America needed cable, and Roebling needed a factory that could produce it at scale. That's why Trenton. Canal access for shipping raw materials in and finished rope out. Rail connections to reach every market in the expanding nation. Room to grow without being hemmed in by existing development. In 1848, he moved his operation to Chambersburg, now part of Trenton, and built the John A. Roebling's Sons Company. The name would become legend. The factory would become the largest wire rope plant in the world. The location was perfect. The Delaware and Raritan Canal brought Pennsylvania coal and iron ore. The rail lines connected to every major city on the eastern seaboard. And the land was cheap enough that Roebling could afford to expand as orders came in. He started small. 85 male employees, 10 of them children under 16. This was 1848, and child labor was just how industry worked. Small hands for small work. Nobody questioned it. The factory ran 6 days a week, making rope for suspension bridges and canal systems. By 1869, Roebling was designing the Brooklyn Bridge when a ferry crushed his foot at a dock in Brooklyn. The toes were amputated. Tetanus set in. 10 days later, he was dead from lockjaw, leaving the bridge project to his son Washington and the wire rope company to his 3 sons, Washington, Ferdinand, and Charles. But the early machines were small, horizontal, limited. They could make rope, but not the kind of rope that could hold the Brooklyn Bridge. Not yet. That would take his sons. That would take engineering that hadn't been invented. And that would take a machine tall enough to become architecture. What they didn't know yet was that the machine they'd build would demand more than space. It would demand blood. The vertical beast, Charles Roebling, graduated from Rensselaer Polytechnic Institute in 1871 as a civil engineer. His father, John, had died 2 years earlier from tetanus after a ferry crushed his foot while surveying for the Brooklyn Bridge, a project that would be completed by Charles's older brother Washington, who himself would be crippled by Caisson disease and confined to his apartment, directing construction through his wife Emily's relay of orders. The Roebling family didn't build small, and they didn't build safe. They built what worked. By the 1880s, the company was churning out wire rope for everything. Bridges, yes, but also shipping, railways, the brand-new elevator industry, telegraph lines strung across continents. The Civil War had proven the value of wire rope for military applications, portable bridges, ship rigging, cable for pontoon systems. After the war, the demand only grew. Railroads needed cable for inclined planes. Cities needed it for early streetcar systems. The mining industry, coal in Pennsylvania, silver in Nevada, copper in Michigan, devoured rope by the mile. In San Francisco, cable cars were eating through rope so fast that the demand was creating an entire sub-industry. Andrew Halidia, who'd built the first cable car line in 1873, was himself a wire rope manufacturer. His father had been in the business in Scotland, and even his own production couldn't keep up. The problem was length. Cable car systems needed ropes thousands of feet long, continuous, without splices. A splice was a weak point. A weak point was a lawsuit waiting to happen, or worse. The cable cars were already dangerous enough. In 1926, a runaway cable car on California Street in San Francisco would crash through a meat truck, spraying passengers with entrails before injuring 106 people. The rope held that day. When it didn't hold, people died. Typical cable car rope life in the 1880s was measured in months, not years. 90 to 180 days of constant gripping, releasing, bending over sheaves, friction against the grip mechanism. The demand was voracious. Some systems burned through 115,000 to 230,000 feet of rope annually. Every foot had to be perfect. The cable car boom created a technical arms race among wire rope manufacturers. Thomas Seal, working as construction engineer for Leland Stanford's California Street Line in 1885, developed the 6x19 Seal construction, a rope design that put the largest wires on the outside of each strand for better abrasion resistance. James Stone improved on Seal's design in 1889 with the 6x25 filler wire construction. Each innovation extended rope life by weeks or months, and each innovation was worth a fortune in contracts. Charles Roebling saw the demand, and he saw the limitation. The horizontal rope machines could only make so much rope at a time because they were limited by floor space. You needed room for the spools, room for the strands, room for the closing apparatus. The bigger the rope, the more floor you needed, and eventually you ran out of floor. The answer was staring him in the face every time he looked at the factory ceiling. If you couldn't go out, go up. So Charles went vertical. In 1893, he designed the 80-ton rope closing machine, 64 feet tall, a tower of iron and precision that twisted 6 wire strands around a central core rope, combining all 7 in a forming die to create finished cable through a process called closing. It wasn't a machine you put in a building. It was a machine you built a building around. The concept was brutal in its efficiency. 6 massive spools, each holding tons of wire strand, were mounted vertically on the machine's frame. They rotated around a central axis, feeding strand downward through guides and dies while the core rope fed up through the center. Gravity helped. Friction fought back. The strands twisted around the core at precise angles, angles calculated to distribute load evenly, to prevent individual wires from bearing too much stress, to create a rope that was stronger than the sum of its parts. The forming die at the bottom squeezed everything together, compressing the 7 elements into one unified cable. Then came the pull-out drums, 8 feet in diameter. These wheels didn't just guide the finished rope, they pulled it. The rotation of the drums created tension, dragging the rope off the spools and through the closing apparatus. 30,000 feet of rope could be spun in a single session. No splices, no weak points. One continuous cable ready to hold a bridge or hoist a mine cage 1,000 feet into darkness. 80 tons of wire loaded at once. Workers had to climb the machine to position the spools, threading strands by hand through guides and eyes 60 feet off the factory floor. One mistake, and the strand would tangle. One tangle, and the batch was ruined. Tons of wire turned into scrap. But when it worked, it was perfect. The machine wasn't just large, it was the largest rope closing machine of its time. And the reason it was built wasn't just engineering pride, it was survival. By the 1890s, the Roebling Company was competing not just with American manufacturers, but with German and British wire rope producers who were flooding the market. Longer ropes meant fewer splices. Fewer splices meant stronger cables. Stronger cables meant winning the contracts for the bridges and elevators and mines that were remaking America's landscape. Before Charles designed the 80-ton machine, he'd built a 30-ton rope machine. It worked, but friction at the base created problems. The weight of the spools and the tension of the wire created heat and resistance that limited production. So, for the 80-ton machine, he redesigned the bearing system using massive journals and oil bath lubrication to handle the load. The engineering was cutting edge. The tolerances were tight enough that a mistake in machining could ruin months of work. The Golden Gate Bridge, the George Washington Bridge, the Manhattan Bridge, the Williamsburg Bridge. Every major suspension bridge built in the first half of the 20th century used Roebling cable or cable made by machines inspired by Roebling's designs. But here's the thing about a machine that size. It didn't just make rope, it demanded things. It demanded operators who understood tension and torque. It demanded maintenance that never stopped. It demanded a building that could handle the vibration when all that iron started spinning. And it demanded a company willing to bet everything on the idea that bigger was better. The Roeblings made that bet, and for 50 years the machine paid it back. But keeping it running? That was a whole different war. Feeding the iron tower. The machine ran. That was the easy part. Keeping it running, that was where men earned their wages. Every 6 hours the bearings needed grease. Not a quick squirt from a can. Real grease. Heavy, black, thick enough to coat the moving parts and keep metal from screaming against metal at temperatures that could blister skin. And the bearings didn't stop while you greased them. The machine kept turning. You leaned in close, oil can in hand, while tons of wire spun inches from your face, and you hoped your hand didn't slip. The heat was constant. The friction of wire against wire, strand against die, rope against drum, all of it generated heat. In summer, the factory floor was an oven. Workers stripped to undershirts, sweat pouring, and still the air felt thick enough to chew. In winter, the machine stayed warm, but the factory walls didn't. Condensation dripped. Metal rusted overnight. Every morning, the maintenance crew wiped down the guides to keep the wire from corroding before it even became rope. The temperature inside the forming die could reach 200 degrees Fahrenheit from friction alone. The wire passing through was moving fast enough that if you touched it, it would take the skin off your hand before you could pull back. Workers learned to judge the temperature by sound. When the wire started singing, a high-pitched whine that cut through even the factory noise, it meant things were running hot. Too hot meant the wire could lose temper, lose strength. So they'd slow the pull-out drums, let things cool, then speed back up. The noise was worse. Imagine standing next to a train while it's moving, but the train never leaves. That's what the rope machine sounded like when it was running full tilt. The hum of the spools, the clang of wire feeding through the dies, the bass rumble of the pull-out drums turning. Men shouted to communicate and couldn't hear the answers. Hand signals, pointing, learning to read lips in a language of iron. Hearing damage was universal. After 10 years in the rope shop, most men couldn't hear conversation in a quiet room. After 20 years, some couldn't hear their wives calling from the next room. Nobody talked about it. It was just the cost. You wanted the job, you paid the price. And the wire itself was unforgiving. Each strand was tensioned to specific tolerances. Too loose, and the rope would be weak. Too tight, and the wire would snap during closing, whipping through the factory like a blade. Workers had scars. Everyone did. A broken wire could slice through clothing, skin, muscle if you were standing in the wrong place when it let go. The worst job was spool loading. When the machine needed to be reloaded, every 30,000 feet, every batch, the crew had to stop production, climb the frame, and manually position new spools, weighing hundreds of pounds each. No cranes inside the machine, no hoists, muscle and leverage. You didn't drop a spool. If it fell, it would crash through the factory floor or kill whoever was below, so you didn't drop it. The climb itself was dangerous. 60 feet up on iron rungs, carrying tools, with the residual heat from the last batch still radiating from the metal. In winter, the rungs could be slick with condensation. In summer, they could burn through work gloves. You climbed fast and you climbed careful, and those two things didn't always go together. One worker, interviewed years later, said the machine had a rhythm. You learned it or you left. The sound of the spools told you if the tension was right. The feel of the wire told you if the temperature was climbing. The smell, oil, hot metal, ozone from friction, told you if something was about to break. And if you ignored any of those signals, the machine would teach you the lesson in blood. The operators developed a sixth sense about the machine. They could hear when a bearing was starting to wear. They could feel when the tension was off by a fraction. They could smell when oil was burning somewhere it shouldn't. This wasn't written in any manual. It was passed down from veteran to apprentice, learned through thousands of hours standing next to spinning iron. Roebling employed about 10,000 workers at its peak during World War I across all its Trenton and Kincora facilities. The rope shop wasn't the biggest department, but it was the most feared. Not because the work was harder than steelmaking or wire drawing, but because the machine never forgave mistakes. A steel furnace you could bank, a wire drawing mill you could slow. The rope closing machine, once it was loaded and running, stopping it meant wasting the batch. So you didn't stop it unless something was on fire or someone was dying. The company town of Roebling, built in 1904 to 1905 10 miles south of Trenton, housed nearly 800 families. Charles Roebling designed it himself. 750 brick houses on a rectangular grid, main streets 100 feet wide, London plane trees lining the medians. The houses were rented at below-market rates. The skilled workers got larger homes farther from the mill. The laborers lived closer to the noise. Everyone understood the hierarchy. Men called it the tower. Some called it worse. Few called it by name. Nicknames were a way of controlling fear, and nobody wanted to admit they were afraid of a machine, but they were. For 6 months after it was built, the tower ran like a dream, batch after batch, rope after rope. The company landed contracts for cable car systems in San Francisco, Pittsburgh, Seattle, elevator cables for the first skyscrapers going up in Manhattan, mine hoists for the coal fields of Pennsylvania and the metal mines out west. Every order met, every deadline beaten. The operators developed superstitions. Don't whistle near the machine. Don't start a batch on Friday the 13th. Don't talk about accidents while the tower is running. Stupid stuff, probably. But when you're standing next to 80 tons of spinning wire, you take comfort where you can find it. And then winter came, and with it, the cold that makes steel brittle and men careless. That's when the tower showed what it could do when things went wrong. But the real test wouldn't come in Trenton. It would come in Brooklyn, where Roebling wire was being used to build the longest suspension bridge the world had ever seen. And when the wire snapped, everyone would learn what tension really meant. The day the wire screamed, February 1878. Brooklyn Bridge construction, not Trenton. This was on site over the East River. But the wire was Roebling wire, spun in Trenton, and what happened that day sent a message back to the factory that nobody forgot. One of the cable strands snapped loose from the Manhattan anchorage. Not a full cable, just one strand, one of the 19 that would eventually make up each main cable. But one strand of Roebling wire under tension is a weapon. It whipped across the construction site like a bullwhip made of steel. Thomas Blake died instantly. The wire struck his forehead and split it open. Harry Supple, a worker from Newfoundland, was knocked from the scaffolding and fell into the East River. 2 other workers were injured. A woman walking on the street below fainted from fright as the wire crashed into buildings, shattering windows. The investigation found the problem. Not the wire, but the temporary fastening. The wire had been secured to the anchorage with a grip that couldn't handle the load. Engineering error, human error, but the wire didn't care why it was loose. It just obeyed physics. Back in Trenton, Charles Roebling received the report. The wire had held. The wire had done exactly what it was designed to do, carry tension until something released it. The problem was the release. Uncontrolled, catastrophic, deadly. He walked through the rope shop that week, watching the tower run, and he understood. Every foot of rope leaving this machine was a potential killer if it failed. Not might be, was. because that rope was going into bridges, elevators, mine hoists, places where failure meant people died. The Brooklyn Bridge project would eventually kill at least 20 workers, possibly 27. Most died from caisson disease, the bends, working in the compressed air chambers underwater. But the wire rope claimed its victims too, and every death carried the Roebling name, whether the company was at fault or not. Some deaths were documented, others weren't. Neil Mullen, an Irish mason and widower with 5 children, died 3 days before Christmas in 1877, when arches supporting the roadway on the Vai, Brooklyn anchorage collapsed. Peter Cope, a German rigger, died in 1873 when his leg caught in a rope that wound around a hoisting engine, crushing his limb and killing him almost instantly. These men had families, they had futures, and they died building something that would outlive them by centuries, held together by wire rope that came out of Trenton. That's when the company started testing. Not just visual inspection, real testing. They built test rigs that could pull rope to destruction, measuring exactly how much load it took to fail. They documented every batch, every spool, every tension setting on the tower. If a rope failed in the field, they wanted to know why, and they wanted to know if it could happen again. The test rig was simple but brutal. A length of rope was secured at both ends and loaded with weight until it broke. The company recorded the breaking load, examined the failure point, and compared it to the theoretical strength calculations. If a batch tested below specification, the entire production run was scrapped, no exceptions. But testing couldn't stop sabotage. In 1878, the same year as the Blake Supple accident, another problem emerged. The J. Lloyd Hay Company had been supplying substandard wire for the Brooklyn Bridge cables. Not Roebling wire, competitor wire, cheap, weak, potentially catastrophic. When the deception was discovered, there was panic. How much bad wire was already in the cables? Could the bridge be trusted? Washington Roebling, still directing construction from his sickbed, ran the calculations. The inferior wire left the bridge only 4 times as strong as necessary instead of 6 to 8 times. Acceptable, barely. But Roebling insisted on adding 150 extra wires to each cable just to be safe. The Hay Company was forced to pay for the replacement wire. Roebling won the contract to supply the additional wire, and the tower ran overtime to produce it. But the incident taught the company something darker. The rope they made was so critical to American infrastructure that failure wasn't just mechanical. It was political, legal, financial. Every rope that left the factory carried liability. Every splice, every strand, every foot had to be perfect because imperfection could bankrupt the company or fill a courtroom with widows. So they ran the tower harder, longer batches, tighter quality control. And they hired men who understood that the machine wasn't just making rope, it was making the framework of trust that held the country's ambitions in the air. The machine ran for decades. Through the construction of the Williamsburg Bridge in 1903, the Manhattan Bridge in 1909, the George Washington Bridge in the 1920s, and in 1935, the big one, the Golden Gate. The Golden Gate Bridge contract was enormous. Roebling was hired to spin the cables, 80,000 miles of wire twisted into cables 36 inches in diameter. The company developed a split tram system, 2 spinning wheels working simultaneously to speed the process. They finished 8 months ahead of schedule, 4 times faster than projected. And the wire that fed those spinning wheels spun in Trenton, spun on the tower and machines like it. The cable spinning for the Golden Gate began in October 1935. Workers used a technique Roebling had perfected over decades, parallel wire construction. Individual wires, each less than 0.2 inches in diameter, were pulled across the span one at a time, bundled into strands, and compressed by hydraulic jacks. Each of the 2 main cables would contain 27,572 parallel wires. Eventually, the Roebling crew devised a system to spin 6 wires simultaneously, color-coded to prevent confusion. In good weather, the spinning wheels took just 6.5 minutes to travel halfway across the span. May 20th, 1936. The last wire was pulled across the bridge, the spinning wheel festooned with flags. 8 months ahead of schedule, the cables were perfect, but the bridge still needed to be finished. February 17th, 1937. A scaffold collapsed. 12 men plunged into the cold Pacific. 10 died. The safety net that had saved 19 workers earlier, the men who formed the Halfway to Hell Club, couldn't hold the weight of the falling platform. It shredded. 2 men survived. 10 didn't. But the cables held. The cables have held for 90 years since. Roebling wire, Roebling tolerances, Roebling reputation. The tower kept running, but the world it was built for was changing. Where the iron sleeps. The machine ran until 1968, 75 years of continuous operation, feeding America's rise into the sky. In 1968, the Roebling Company modified the tower one last time, reconfiguring it to produce 5-inch wire rope, the largest diameter rope made at the time, for surface mining operations, strip mines, drag lines, machines that could move mountains and needed cables strong enough to prove it. But by then, the writing was on the factory wall. The company had been sold to Colorado Fuel and Iron in 1952. The new owners didn't have the same attachment to Trenton, to the legacy, to the idea that bigger was better. They saw overhead, aging equipment, cheaper production elsewhere. The Roebling family was out. After 103 years of family control, the company was just another asset on a balance sheet. In 1974, the Roebling Works in Trenton shut down for good. 10,000 workers at peak employment, gone. The factory that had built the cables for the Brooklyn Bridge, the George Washington Bridge, the Golden Gate, silent. The workers walked out for the last time carrying lunch pails and memories. Some had worked there for 40 years. Their fathers had worked there. Their grandfathers had worked there. 3 generations of families tied to the same factory, the same machines, the same wire. The tower remained, too large to dismantle easily, too expensive to scrap. It sat in the factory building, rusting, as the years passed and the factory itself decayed. Pigeons nested in the rafters. Rain leaked through the roof. The pull-out drums, once polished by constant use, grew a skin of rust. In 1989, the American Society of Mechanical Engineers designated the 80-ton rope-closing machine a National Historic Mechanical Engineering Landmark. It's the only remaining Roebling machine. Everything else was scrapped, sold, demolished. The tower survived because removing it would have required demolishing the building around it. Today, it sits in what's now the Roebling Museum in Trenton, part of a redevelopment effort to preserve the industrial heritage of the site. You can walk into the building and see it. 64 feet of iron and history, still bolted to the floor, still integrated into the architecture. The machine will never run again. But it doesn't need to. It already did its job. Every suspension bridge built in America before 1950 used Roebling wire rope or rope inspired by Roebling's methods. Every elevator cable that lifted office workers in the first skyscrapers, every mine hoist that brought coal and metal out of the earth, every tramway, every cable car, every application where failure meant death, Roebling rope held them. The company's reach extended beyond bridges. During World War I, Roebling produced submarine netting for the North Sea mine barrage, thousands of miles of steel cable strung across the ocean to trap German U-boats. The Spirit of St. Louis, Charles Lindbergh's plane, used Roebling wire for control cables and wing braces. The Panama Canal construction relied on Roebling rope for drag lanes and excavators, ski lifts, tramways, oil drilling. Anywhere tension and strength mattered, Roebling was there. The Golden Gate Bridge still stands. Its original cables, spun with Roebling wire in 1935 to 36, are still in service, inspected constantly, maintained religiously, but holding. After 90 years of fog, wind, earthquakes, and traffic, the wire still does what Charles Roebling designed it to do. carry the load without breaking. The Brooklyn Bridge still stands. Finished in 1883, it's been carrying traffic for 143 years. The cables Washington Roebling oversaw, made with his father's wire, twisted on machines Charles would later perfect, still holding. What killed the Roebling Company wasn't failure, it was success. They'd built the infrastructure of modern America, and by the mid-20th century, that infrastructure was complete. The big bridges were built. The skyscrapers had their cables. The mines had their hoists. The demand shifted to maintenance, to replacement, to smaller orders that didn't need a 64-foot machine to fulfill. Diesel came. Smaller, cheaper, lighter wire rope from competitors who didn't have the overhead of maintaining a factory the size of a city block. Automation came. Computer-controlled rope machines that could match the tower's output with a tenth of the floor space. By 1974, the tower was obsolete, not because it couldn't do the job, but because the job no longer needed to be done at that scale. The building still stands in Trenton. Parts of the factory complex have been converted to lofts, offices, commercial space. The Roebling Museum occupies the old machine shop, preserving the history of a company that employed 10,000 people and built the framework for America's vertical ambitions. You can visit the tower, stand next to it, look up at 64 feet of iron, and try to imagine what it sounded like when it was running full tilt, spools spinning, wire feeding, pull-out drums turning, and 30,000 feet of cable being borne. The guides still bear the wear marks from millions of feet of wire. The pull-out drums still show the grooves where rope wrapped around them for 75 years. The forming die at the bottom, where 7 strands became one, is still there, frozen in the position it held when the last batch was finished in 1968. What the tower accomplished wasn't just mechanical, it was trust. When you rode an elevator in 1920, you trusted Roebling cable not to drop you. When you drove across the Golden Gate in 1937, you trusted Roebling wire not to let the bridge fall. When miners descended into the earth, they trusted Roebling rope not to send them to the bottom in a screaming tangle of broken cable and shattered bodies. That trust was built one batch at a time, one 30,000-foot spool at a time, in a machine so large it had to become part of the building, operated by men who understood that their work wasn't just making rope, it was holding the country together. The tower sits silent now, but every bridge cable you see, every elevator you ride, every structure held aloft by twisted wire, that's the tower's legacy, not retired. Everywhere we look at the Golden Gate and see paint and towers, but it's not a bridge. It's a testament to the men who believed they could span the impossible, held up by wire rope that came out of a machine in Trenton that was too big to fit in a normal building. We look at the Brooklyn Bridge and see history, but it's not history. It's still holding traffic, still proving every single day that John Roebling's vision of wire rope was right, that his son's engineering was sound, that the tower did its job. They don't make machines like that anymore. Not the size, not the commitment, not the idea that sometimes the only way to build what the future needs is to make the machine part of the architecture. And they don't make men like that anymore either. The ones who stood next to 64 feet of spinning iron day after day, knowing that if they made a mistake someone might die. Not might, would. And they showed up anyway. Because the rope had to be made. Because the bridges had to be built. Because the country needed to rise, and someone had to make the cable that would hold it in the air. The tower made that cable, and the men who ran it made sure it never broke. Progress has a price. The Roeblings paid it in full.